I want to ask you something, and I want you to think about it very carefully before you answer. What shape is the Earth? Go on, say it. You said round, didn't you? Or maybe a sphere. Perhaps you even said a ball. And you said it with complete confidence, the way you'd say the sky is blue or fire is hot. You learned it in school, you've seen the photographs from space, you bet your house on it. The Earth is round, obviously, everyone knows that. Except it isn't. Not a sphere, not a ball, not even close to round in the precise mathematical, physical sense of the word. And I'm not talking about mountains and valleys and surface bumps. I'm not playing a cheap word game with you. I'm telling you something genuinely, deeply, physically, true something that changes how you understand gravity, how you understand the structure of planets, how you understand the very forces that shaped every world in this solar system. The Earth is bulging at its equator, flattened at its poles, lumpy with invisible mass concentrations, and bent by the very fabric of space-time in ways that make round not just imprecise, but completely fundamentally wrong. Today I'm going to show you exactly why, and it is going to be wonderful. Let me start with mathematics, because in physics, if you want to say something precise, you use mathematics. And if you want to say something is round, if you want to actually mean something by that word, you need to define it mathematically. A perfect sphere. That's what most people picture when they think of the Earth from space. A perfect sphere is a geometric object defined by a single beautiful property. Every point on its surface is exactly the same distance from the center. Every single point. No exceptions. The radius is constant the same in every direction, whether you measure from the North Pole or the South Pole or the equator or anywhere in between. That is a sphere. And here is the first and most fundamental thing I want to tell you. The Earth is not a sphere by this definition, not even approximately. The Earth fails this definition in a way that is not subtle, not a matter of measurement precision, and not something you can wave away as an engineering approximation. The Earth fails the definition of a sphere in a way you can measure with a tape measure, a way that changes the outcome of physics experiments, a way that affects GPS, satellites, and ocean tides, and the trajectory of ballistic missiles, and the orbit of every spacecraft we have ever launched. So let's talk about the real shape of the Earth. And to understand it, I need to tell you about two forces that were arm wrestling with each other while the Earth was forming. About 4.5 billion years ago, when the solar system was young and everything was molten rock and chaos and collision. Force number one, gravity. Gravity is the great sculptor of worlds. It pulls everything toward everything else. It pulls every atom of rock toward every other atom of rock. And if gravity were the only force acting on a planet, if a planet were sitting perfectly still in space, rotating not at all, then gravity would sculpt that planet into a perfect sphere. Because a perfect sphere is the shape where every bit of mass is as close as possible to every other bit of mass. Gravity loves spheres. A non-rotating planet, given enough time, would be a perfect sphere. But force number two, rotation. The Earth is spinning. It has been spinning since it formed. And it's still spinning right now, one full rotation, approximately every 24 hours. And rotation introduces centrifugal effects. Now, I know some physicists get squeamish when I say centrifugal force. They prefer to call it a fictitious force in the rotating frame of reference, but let's not get pedantic. The effect is real. When you spin a bucket of water on a string, the water pushes outward against the bucket. When you spin the Earth, the material of the Earth pushes outward, away from the rotation axis. And this centrifugal effect is not uniform. It depends on distance from the rotation axis. At the poles at the very top and bottom of the Earth, sitting right on the rotation axis, the centrifugal effect is zero. You're spinning, but you're spinning in place, like a top spinning on its point. There's no outward push at all. But at the equator, at the fat middle of the Earth, as far from the rotation axis as you can get, the centrifugal effect is at its maximum. Every bit of material at the equator is moving in a circle of maximum radius, and it wants to fly outward. Gravity is pulling it inward, the rotation is pushing it outward, and the equilibrium position, the shape where these two effects balance, is not a sphere. The equilibrium shape of a rotating body under its own gravity is a shape called an oblate spheroid, not a sphere, an oblate spheroid. This is a shape like a sphere that someone has sat on, squashed at the top and bottom, bulging around the middle. Technically, it's a solid of revolution formed by rotating an ellipse around its shorter axis. Technically, it's a shape characterized by two different radii, the equatorial radius and the polar radius. And here are the actual numbers for the Earth, real, measured, experimentally verified numbers that you can check in any physics reference. The equatorial radius of the Earth, the distance from the center to the equator, is approximately 6,378 kilometers. The polar radius, the distance from the center to either pole, is approximately 6,356 kilometers. The difference? 22 kilometers, more than 13 miles. The Earth is 22 kilometers fatter at its equator than at its poles. Let me give you a feel for how significant this is. If you built a scale model of the Earth that was exactly 1 meter across a perfect scale model, every dimension shrunk by the same factor, the equatorial bulge would be a difference of about 3.4 millimeters. That doesn't sound like a lot, but it is measurable by eye if you look carefully. And at the actual scale of the Earth, 22 kilometers is not subtle. 22 kilometers is the height of Mount Everest, more than twice over. Because of this equatorial bulge, Mount Everest, despite being the highest point above sea level, is not the farthest point from the center of the Earth. Mount Everest sits at about 28 degrees north latitude, nowhere near the equator. The actual farthest point from the center of the Earth is the peak of a mountain called Chimborazo in Ecuador, which sits almost exactly on the equator. Chimborazo is only about 6,268 meters above sea level, much shorter than Everest, but because it sits on the equatorial bulge, its summit is about 6,384 kilometers from Earth's center. Everest summit is about 6,382 kilometers from Earth's center. Chimborazo wins, not because it's taller above sea level, but because it's sitting on a fatter part of the Earth. This is not a curiosity. This is a fundamental physical fact that affects real measurements. Because the Earth is an oblate spheroid and not a sphere, the strength of gravity at the Earth's surface varies with latitude. At the poles, you are closer to the center of the Earth. The full mass of the Earth is closer to you. And additionally, there is no centrifugal effect working against gravity. At the equator, you are farther from the center, and the centrifugal effect of rotation is pushing you away from the center. The combined result is that gravity is measurably stronger at the poles than at the equator. The difference is about 0.5%, not enormous, but absolutely measurable. If you very carefully weighed a precision mass at the North Pole and then flew it to the equator and weighed it again, you would get a different weight. The mass would be the same mass, doesn't change, but the gravitational force on it would be measurably less at the equator. This is a real, measured, experimentally confirmed fact. Gravity varies with latitude because the Earth is not a sphere. Now you might be thinking, okay, fine, the Earth is an oblate spheroid instead of a sphere. That's a small correction to the basic spherical picture. It's still basically round, and I say to you, we haven't even started. The oblate spheroid is just the first level of approximation. When you look more carefully, when you make more precise measurements, you find that the Earth deviates from an oblate spheroid in ways that are even more interesting and more physically meaningful. Let me introduce you to the actual, official, scientifically defined shape of the Earth. It has a name, geodesists. The scientists who study the precise shape of the Earth call it the geoid. The geoid is defined as the surface of equal gravitational potential that most closely matches the mean sea level of the world's ocean. It is the shape the surface of a planet-wide ocean would take if the ocean covered the entire Earth and the water was perfectly still, no waves, no tides, no currents, and the geoid is not an oblate spheroid. The geoid is lumpy, irregular. It varies from the idealized oblate spheroid by up to about 85 meters in some places. In some regions, the geoid bulges outward from the oblate spheroid. In other regions, it dips inward. These lumps and dips in the geoid correspond to variations in the density of the material beneath the surface, places where there are concentrations of particularly dense rock or voids, or different geological structures that create local variations in gravitational pull. The geoid is the true gravitational shape of the Earth, and it looks like a slightly misshapen potato, a very, very nearly spherical potato, yes, but a potato nevertheless, not a sphere, not an oblate spheroid, a lumpy, irregular, geophysically complex shape that can only be described by a complicated mathematical function involving thousands of terms. So the next time someone tells you the Earth is round, tell them, approximately. Tell them it's an oblate spheroid to first approximation and a geoid when you get serious about it. And tell them that the difference matters, that it matters for GPS satellites, for ocean currents, for gravity measurements, for space flight, and for a dozen other things we're going to explore in the parts ahead. But we have barely scratched the surface, because so far I've only been talking about the Earth's shape as a static object. I haven't talked about what's happening to the shape over time, the way the Earth is still deforming from the last ice age, the way the tides pull it into an ellipsoid oriented toward the moon, the way it vibrates and rings like a bell after earthquakes. The Earth is not a static solid object. It is a dynamic, flowing, constantly changing system, and its shape is part of that dynamism. I want to talk about spinning, because spinning is one of the most underrated, most consequential, most physically rich phenomena in the universe. Spinning stars, spinning galaxies, spinning tops, spinning electrons, rotation is everywhere in physics, and it does extraordinary things to matter. Let me start with something simple and personal. Have you ever been on a merry-go-round? Not a modern, safety-oriented playground merry-go-round, but one of the old fast ones, the kind that if you grabbed the outside rail and ran and jumped on, it would spin you fast enough to make your stomach drop. Do you remember that feeling? The feeling of being pressed outward, away from the center, that pressing feeling, that's the centrifugal effect. And it's the same effect that is squashing the Earth into an oblate spheroid right now, as you sit there. But before I go deeper into what spinning does to the Earth, I want to talk about a question that I find absolutely wonderful, because it has an answer that surprises most people. Why is the Earth spinning in the first place? Where did the spin come from? Why isn't the Earth just sitting still? The answer goes back to the formation of the solar system. About 4.5 billion years ago, the solar system began as a vast, diffuse cloud of gas and dust, hydrogen and helium, and heavier elements forged in the depths of earlier stars. This cloud started to contract under its own gravity. As it contracted, it started to spin. Why? Because of the conservation of angular momentum, one of the most fundamental conservation laws in all of physics. Here's the idea. Angular momentum, the spinning momentum of a system, is conserved when there are no external torques. This is not an approximation. This is not roughly true. This is exactly, precisely true to the best of our ability to measure it. The angular momentum of an isolated system never changes. Now, any large cloud of gas will have some small, random rotation just from the random motions of its constituent particles. The net angular momentum might be small, but it's not zero. As the cloud contracts as gravity pulls it inward, reducing its radius, conservation of angular momentum demands that the rotation rate must increase. Just as an ice skater pulls her arms inward and spins faster, the contracting gas cloud spins faster as it gets smaller. By the time the gas cloud had collapsed into the flat disk of the solar system, and by the time the disk had clumped together into the sun and the planets, all that angular momentum was distributed throughout the system. The planets formed out of swirling material, and they inherited the angular momentum of the material they formed from. The Earth spins because the clump of material that became the Earth was itself rotating as it came together, and angular momentum is conserved. This is beautiful. The fact that the Earth rotates once a day is a direct consequence of the rotation of a molecular cloud that existed before the sun was born. Your day-night cycle is a direct inheritance from conditions that existed 4.5 billion years ago, before the Earth even existed. That's conservation of angular momentum in action. Now, what does the Earth's rotation actually do to its shape? I gave you the basic answer in part one. It creates an equatorial bulge. But I want to go deeper, because the physics of a rotating, self-gravitating body is exquisitely interesting. Consider this. What is the equilibrium shape of a rotating ball of fluid? This is a question that Isaac Newton himself worked on. He used his theory of gravity and his understanding of mechanics to predict the equatorial bulge of the Earth before it was accurately measured. He calculated that the Earth should be approximately 1 over 230 times wider at the equator than at the poles. That is, the difference between equatorial and polar radius should be about 1 over 230 of the polar radius. The actual measured ratio turns out to be about 1 over 298. Newton was in the right ballpark, though not exactly right. Getting closer required better understanding of the Earth's internal structure and density distribution, which Newton didn't have. But the point is, the rotation-induced shape of a planet is predictable from physics. If you know the mass of a planet, its rotation rate, and something about how its mass is distributed internally, you can calculate what shape it should be. And this works. We can calculate the shapes of Jupiter, Saturn, Uranus, Neptune, and compare those calculations to our measurements, and the physics comes out right. Now, Saturn is a particularly striking case. Saturn rotates once every 10.7 hours, much faster than the Earth's 2-4-hour rotation. And Saturn is a gas giant. Unlike Earth, it has no solid surface to maintain a rigid shape. The result? Saturn's equatorial bulge is enormous. Saturn's equatorial radius is about 60,268 kilometers, while its polar radius is only about 54,364 kilometers. The difference is nearly 6,000 kilometers, a difference of about 10%. Saturn is dramatically, obviously, visually non-spherical. If you look at photographs of Saturn, and I encourage you to do this, because it is one of the most beautiful things you will ever see, you can actually SEE that it's flattened. It looks like someone very gently pressed on the top and bottom. Now back to Earth. I want to tell you about some of the remarkable physical consequences of the Earth's non-spherical shape. Here is one that I find delightful. The equatorial bulge of the Earth causes the axis of the Earth to precess. What does that mean? The Earth's rotation axis is tilted at about 23.5 degrees from the perpendicular to its orbital plane. This tilt is what gives us the seasons, but because the Earth has an equatorial bulge, and because the Moon and Sun exert gravitational forces on that bulge, the Earth's rotation axis doesn't just sit still. It slowly traces out a circle in space, like a spinning top that's slowly wobbling. This precession takes about 26,000 years to complete one full cycle. This has profound consequences for the long-term history of Earth's climate. The direction in which the Earth's axis points, and therefore which part of Earth's orbit corresponds to summer for the northern hemisphere, changes slowly over this 26,000-year cycle. Combined with other orbital variations, this precession of the Earth's axis drives the Milankovitch cycles, the periodic variations in Earth's climate that are responsible for the coming and going of ice ages over geological time. The ice ages that covered North America and Europe in kilometers of ice, they were driven in part by the precession of the Earth's rotation axis. And that precession is caused by the gravitational forces of the Moon and Sun acting on the equatorial bulge, which is itself a consequence of the fact that the Earth is not spherical. So the shape of the Earth, this deviation from a perfect sphere, has determined the rhythm of ice ages over millions of years. The non-spherical shape of the Earth is not an obscure technical correction. It is woven into the deep history of climate, of evolution, of the comings and goings of glaciers that carved the landscape of entire continents. Here is another consequence. Satellites. Every satellite orbiting the Earth, every GPS satellite, every weather satellite, every spy satellite, every piece of space debris has its orbit affected by the Earth's equatorial bulge. A perfectly spherical Earth would produce perfectly stable orbital planes. Satellites would orbit in the same plane forever, and the direction of that plane in space would not change. But the Earth is not a perfect sphere. The equatorial bulge creates a gravitational field that is not perfectly uniform in direction. For satellites whose orbit is inclined to the equator, which is most of them, this non-uniform gravity causes the orbital plane to slowly rotate. Orbital mechanics engineers call this nodal precession, or regression of the node. The rate at which a satellite's orbital plane precesses depends on the inclination of the orbit and the altitude of the satellite, and it can be calculated precisely using a parameter called J2, the second-order coefficient of the spherical harmonic expansion of the Earth's gravitational potential, which is basically a way of mathematically encoding how non-spherical the Earth is. This is not an abstract concern. Every time you use GPS, the ground stations that monitor and correct the GPS satellites are accounting for nodal precession. The equations that control station keeping for the International Space Station account for the Earth's non-spherical gravitational field. The fact that the Earth is not round is a practical engineering reality that affects every piece of technology that operates in Earth orbit. And there is one special class of satellite for which the Earth's equatorial bulge is not a nuisance but a beautiful opportunity. Sun-synchronous orbits. If you choose the right altitude and inclination for a satellite orbit, the nodal precession caused by the equatorial bulge can be tuned to exactly match the rate at which the Earth orbits the Sun, about 1 degree per day. A satellite in a sun-synchronous orbit precesses at exactly this rate, which means it always crosses the equator at the same local solar time. The satellite sees the Earth below it, always lit at the same angle by the sunday. This is enormously useful for Earth observation satellites, weather satellites, reconnaissance satellites, environmental monitoring satellites, sun-synchronous orbits exist because the Earth is not round. The non-spherical shape of the Earth is not a flaw. It is not a correction to an otherwise perfect system. It is a fundamental physical feature with profound consequences at every scale, from the ice ages that shaped human evolution to the GPS technology in your pocket. I want to introduce you to a word that most people have never heard, and that I think is one of the most beautiful words in all of geophysics. The word is geoid, G-E-O-I-D. And the geoid is the true, honest, physically real shape of the Earth. Not the simplified sphere we teach in grade school, not even the oblate spheroid that Newton could calculate, but the actual gravitational surface that determines where the oceans sit, how water flows, and how every object on Earth falls. Let me define it carefully, because the definition is where the beauty lives. The geoid is the surface of equal gravitational potential, what physicists call an equipotential surface, that most closely matches the mean sea level of the world's ocean. Another way to say it, the geoid is the shape that the surface of a worldwide, perfectly still ocean would take. Why is that the true shape? Because gravity determines everything. Gravity is the dominant force on Earth's surface. Gravity is what makes things fall, what makes rivers flow downhill, what makes the oceans collect in the lowest gravitational potential regions. The geoid, the gravitational equipotential surface, is the surface of constant gravitational potential, which means that things on the geoid have no tendency to slide in any horizontal direction. Water doesn't flow on the geoid because there's no downhill. Everything is at the same gravitational height. This is why sea level is the standard reference. Not because the ocean surface is a perfect geometric shape, but because the ocean surface is very approximately the geoid. The ocean has settled into the gravitational equilibrium surface. Now here is where it gets genuinely strange. The geoid is not an oblate spheroid. It is not a smooth, mathematically simple shape. It is bumpy, lumpy, irregular. The geoid varies from the best fit oblate spheroid by up to about 85 meters. In some places, the geoid rises about 85 meters above the spheroid over parts of the North Atlantic and dips about 105 meters below the spheroid south of India in the Indian Ocean. The biggest dip in the geoid on Earth, the most dramatic gravitational low point, is a region south of India in the Indian Ocean. Geodesists have somewhat gleefully nicknamed it the Indian Ocean geoid low, or sometimes, less formally, the gravity hole. In this region, the geoid is about 106 meters below the reference spheroid. If you took a worldwide ocean of perfectly still water and looked at it in this region, the sea surface would be approximately 106 meters lower than you'd expect based on the spheroid shape alone. This is not a hole in the ocean floor. The bathymetry of the ocean floor in this region is quite normal. It's a hole in gravity. The gravitational potential is anomalously low in this region. Why? Because there is a deficit of mass below this region. The mantle material under the Indian Ocean low is, for reasons related to the complex history of mantle convection and plate tectonics, less dense than average. Less mass means weaker gravity. Weaker gravity means the equipotential surface dips lower in this region. The shape of the Earth, as measured by gravity, reflects the distribution of mass inside the Earth, not just at its surface. This is the deep point. The geoid is a map of the interior of the Earth. The lumps and bumps and dips in the geoid tell you about the distribution of dense and less dense material all the way down through the mantle and even through the core. By precisely measuring the geoid, by mapping the gravitational equipotential surface with extraordinary precision, we learn about the interior structure of the Earth without ever drilling a hole deeper than about 12 kilometers, which is the deepest humans have ever drilled, and yes, that is tiny compared to the Earth's radius of 6,371 kilometers. How do we measure the geoid? With satellites. Specifically with missions like GRACE, the Gravity Recovery and Climate Experiment, and its successor GRACE-FO. These missions used two identical satellites flying in tandem, separated by about 220 kilometers in the same orbit. As the two satellites flew over regions of higher or lower gravity, the slight variations in gravitational pull changed the distance between them by tiny amounts as small as a few micrometers. By measuring these tiny changes in satellite separation with extraordinary precision, the GRACE mission mapped the Earth's gravitational field, and therefore the geoid, with unprecedented accuracy. And the GRACE measurements are beautiful. The geoid maps produced by GRACE look like a lumpy, slightly squashed ball with all manner of bumps and hollows. You can see the gravitational signatures of ocean trenches and mid-ocean ridges. You can see the gravitational signatures of mountain ranges. The Himalayas create a positive gravity anomaly because of their enormous mass. You can see the gravitational signatures of ancient Ice Age glaciers. The regions of Canada and Scandinavia that were covered by kilometers of ice during the last Ice Age are still, thousands of years later, bouncing back up as the ice load has been removed. This glacial isostatic adjustment is still ongoing, and the GRACE satellite can see it in the changing shape of the geoid over time. I want to dwell on that last point because it brings out something wonderful about the Earth's shape. It changes. The Earth's shape is not fixed. It is not permanent. The Earth is not a solid, rigid ball that holds its shape eternally. The Earth is a complex, dynamical system that is constantly deforming in response to forces that act on it. The glacial isostatic adjustment I mentioned is one example. The great ice sheets of the last Ice Age, which at their maximum covered about 30% of the Earth's land surface in ice, up to 3 kilometers thick, pressed down on the continents beneath them. The weight of all that ice pushed the solid rock of the Earth's crust downward into the mantle below. When the ice melted about 10,000 to 20,000 years ago, the ice load was removed, and the crust slowly started rising back up like a foam cushion, recovering after you stopped sitting on it. This process is called post-glacial rebound or glacial isostatic adjustment. It is still happening today. Scandinavia is currently rising at a rate of about 1 centimeter per year. Canada is rising. These changes are measurable. The shape of the Earth is measurably different today from what it was 10,000 years ago, and it will be measurably different again 10,000 years from now. There are other dynamic changes in the Earth's shape as well. The oceans themselves deform the geoid as ocean currents move warm, less dense water around the planet, or as sea levels rise due to melting ice. The distribution of mass at the surface changes, and the geoid changes with it. When a major earthquake occurs, a large subduction zone earthquake, like the 2004 Indian Ocean earthquake or the 2011 Tohoku earthquake in Japan, the redistribution of rock during the fault rupture actually changes the Earth's gravitational field measurably. The Earth's rotation rate changes slightly. The position of the Earth's rotation axis shifts slightly. The geoid changes. Major earthquakes literally, measurably, physically reshape the Earth. And there is the tidal deformation. Every day, as the moon orbits the Earth, its gravitational pull flexes the solid Earth. We talk about ocean tides, the rising and falling of sea level as the moon's gravity pulls the water, but there are also solid Earth tides. The solid rock of the Earth actually bends and deforms in response to the moon's tidal forces. The magnitude of this solid Earth tide is about 30 centimeters. The ground you are standing on moves up and down by about 30 centimeters twice a day in response to the moon's gravity. You don't feel it because everything around you is moving with you, but it is real and measurable with precise instruments. The Earth is an oblate spheroid, adjusted by the geoid, dynamically deforming under the influence of tides, earthquakes, glacial rebound, and the shifting of masses across its surface. It is a living, breathing, changing shape, not the static blue marble of the famous Apollo photograph, but a complex, dynamic, physically rich object that is never quite the same shape twice. Now I want to talk about something that takes the whole question of the Earth's shape to a completely different level, because so far we've been talking about the Earth's shape in the traditional sense as a three-dimensional geometric object that occupies three-dimensional space. And what we found is already surprising. It's not a sphere, it's an oblate spheroid. And more precisely, it's a geoid, a lumpy, irregular gravitational equipotential surface. But Einstein showed us that three-dimensional space is not the full story. Space is not flat. Space is not Euclidean. Space is curved. And the curvature of space around the Earth is part of what shape means at the deepest physical level. Let me back up and explain what I mean by space-time curvature, because I want to do it right. In Newton's theory of gravity, gravity is a force. Mass creates a gravitational force that attracts other masses toward it. A planet like the Earth sits in flat, three-dimensional Euclidean space, and it exerts a force on objects near it, a force directed toward its center. The moon orbits the Earth because the Earth's gravity pulls it in a curve. An apple falls because the Earth's gravity pulls it down. Einstein replaced this picture entirely. In general relativity, there is no gravitational force. Instead, mass curves space-time, the four-dimensional fabric of space and time. And objects in curved space-time simply follow the straightest possible paths through that curved geometry paths the physicists call geodesics. The moon's orbit is not a curved path caused by a force. It is the straightest possible path through the curved space-time around the Earth. The apple falls not because of a force, but because the straightest path through the curved space-time near the Earth's surface leads downward. This is a fundamentally different picture of gravity, and it changes what we mean by the shape of the Earth. In Newtonian gravity, the Earth has a shape that you can describe with coordinates: latitude, longitude, altitude. The shape is purely geometric. It's about the arrangement of matter in three-dimensional space. But in general relativity, the Earth doesn't just have a spatial shape, it has a space-time shape. The Earth curves the four-dimensional fabric of space-time, and the pattern of that curvature is what we experience as gravity. What does the space-time curvature around the Earth look like? Well, first of all, because the Earth is not spherically symmetric, because it has an equatorial bulge and a lumpy geoid, the space-time curvature around it is also not spherically symmetric. The gravitational field, in the general relativistic sense, is a curved four-dimensional geometry that maps onto the non-spherical mass distribution of the Earth. But the curvature of space-time around the Earth does something else remarkable. It makes time run at different rates at different locations. This is called gravitational time dilation. Clocks in stronger gravitational fields closer to the Earth's surface run slower than clocks in weaker gravitational fields farther from the Earth's surface. This is not a subtle, almost undetectable effect. It is a real, measured, practically important effect. Here are the actual numbers. A clock at sea level runs slower than a clock at the altitude of GPS satellites, about 20,000 kilometers above sea level, by about 45 microseconds per day due to gravity alone. There is a competing special relativistic effect going in the opposite direction. The satellite clocks also tick slower because they're moving faster than clocks on the ground, but that effect is smaller, about 7 microseconds per day. So the net effect is still about 38 microseconds per day of the satellite clocks running faster than ground clocks. 38 microseconds per day. That doesn't sound like a lot. But GPS works by measuring the travel time of radio signals from satellites to your receiver with extraordinary precision. Light travels about 11.4 kilometers in 38 microseconds. If the relativistic correction were not applied, if the GPS clocks were not continuously corrected for the effects of both gravitational time dilation and special relativistic time dilation, the GPS system would accumulate errors of about 11 kilometers per day. Within hours, GPS would be useless. Within days, it would be catastrophically wrong. General relativity is not an abstract academic curiosity. It is an engineering reality that is built into every GPS device you have ever used. Every time your phone navigates you to the right address, it is using general relativistic corrections. Einstein's curved space-time is in your pocket right now, doing real work. But I want to go further. I want to talk about what the curvature of space-time around the Earth means for the concept of shape itself. Here is a thought experiment. Imagine you want to measure the circumference of the Earth at the equator. You set up a measuring tape, an imaginary, arbitrarily long measuring tape, and you wrap it around the Earth's equator and measure the circumference. You get approximately 40,075 kilometers. Now you measure the diameter, the distance from one side of the Earth to the other, passing through the center, approximately 12,756 kilometers. In flat Euclidean geometry, in the geometry of a flat three-dimensional space, the circumference of a circle should be pi times the diameter. Pi times 12,756 kilometers is approximately 40,074 kilometers. That's almost exactly what we measured. So the equatorial geometry seems Euclidean to excellent approximation. But now let's think more carefully. The Earth is in curved space-time. The curvature of space-time is small near the Earth, not negligible, but small. The geometry of space near the Earth is very close to flat, but not exactly flat. The deviation from flat Euclidean geometry is tiny, but it is there. And if you could measure with extraordinary precision, the kind of precision that only comes with careful relativistic calculations, you would find that the relationship between the equatorial circumference and the diameter of the Earth does not exactly satisfy the flat space formula C equals pi times d. The space-time curvature produces tiny deviations. These deviations are small for the Earth, but for much more massive or compact objects, for neutron stars or black holes, the deviations from Euclidean geometry are enormous. For a black hole, the geometry of space near the event horizon is so curved that the usual rules of Euclidean geometry break down completely. And here is a beautiful, mind-bending point about what this means for shape. In ordinary three-dimensional Euclidean space, a sphere is a sphere, a set of points equidistant from a center. You can describe its shape with simple geometry. But in curved space-time, the geometry itself is modified. The concept of distance is redefined by the curvature of space-time. And therefore, the concept of shape, which depends on distances, is also modified. When you ask, what is the shape of the Earth, in general relativity, you are asking a question about the four-dimensional space-time geometry sourced by the Earth's mass distribution. The shape is not just a three-dimensional surface, it is a curvature of a four-dimensional manifold. It is encoded in the components of the metric tensor, the mathematical object that tells you how to measure distances and time intervals in curved space-time. This is not something you can draw a simple picture of, but it is, in a deep sense, the truest and most complete answer to the question, what shape is the Earth? It is not round. It is not an oblate spheroid. It is a particular curved space-time geometry, a four-dimensional curvature of space and time that is described by Einstein's field equations applied to a roughly spherical, slightly oblate, lumpy mass distribution rotating at 1 revolution per day. Compared to that picture, round seems almost comically inadequate. Let me add one more layer to this relativistic picture of the Earth's shape. General relativity predicts that a rotating mass doesn't just curve space-time, it also drags space-time around with it. The way a rotating ball dragged through honey drags the honey. This effect is called frame dragging, or more technically, the Lentz-Thurring effect. The rotating Earth literally drags the fabric of space-time around with it as it spins. This frame dragging is tiny for the Earth, far smaller than the main gravitational time dilation effect, but it is real and it has been measured. A satellite called Gravity Probe B, launched in 2004, carried 4 ultra-precise gyroscopes in Earth orbit and measured the precession of those gyroscopes due to frame dragging. The result confirmed Einstein's prediction to within 19% experimental uncertainty, with later analyses improving this to better than 1%. The Earth's rotation is literally twisting space-time. The shape of space-time around the Earth is not just curved, it is twisted in a way that has been directly measured with gyroscopes in orbit. The Earth's shape, in the fullest relativistic sense, includes this space-time twist. Now, I want to do something that I think is one of the most illuminating things you can do in science: compare, because the Earth doesn't exist in isolation. It is one planet among many, and the other planets in our solar system, with their different sizes, different masses, different compositions, different rotation rates, give us a magnificent natural laboratory for testing our understanding of what determines the shape of a world. Let me take you on a quick tour of the solar system, looking at each world through the lens of the question: how round is it, and why? Mars. Mars is smaller than Earth, less massive, and has a somewhat longer rotation period, about 24.6 hours, barely different from Earth's 24 hours. Because Mars has a longer history of geological quiescence, it has been largely geologically inactive for billions of years, and because its internal heat has largely dissipated, Mars is actually a bit rounder than Earth in proportion to its size. But Mars has its own fascinating shape, irregularity. Mars has a dramatic north-south asymmetry. The northern hemisphere is on average about 3 to 5 kilometers lower in elevation than the southern hemisphere, and the crust is much thinner in the north. The reason for this asymmetry is still debated. It might be the result of a giant impact in the early solar system, or it might be a consequence of mantle convection patterns. But the point is, Mars is emphatically not a sphere. It has a north-south asymmetry that makes it arguably one of the most lopsided planets in the solar system. Mercury. Mercury is the smallest planet, very dense, mostly iron, and rotates extremely slowly. A Mercurian day is about 59 Earth days. This very slow rotation means the centrifugal effect is tiny. Mercury's equatorial radius and polar radius are almost identical. Mercury is the most spherical of all the planets, precisely because it rotates so slowly. The relationship between rotation rate and oblateness is clear. Slow rotation means more spherical. This is exactly what the physics predicts. Venus. Venus rotates even more slowly than Mercury. A Venusian day is actually longer than a Venusian year, and Venus rotates backward relative to most planets. It spins in the opposite direction. Again, slow rotation means Venus is very nearly spherical, its equatorial and polar radii differing by only a few kilometers. And then we get to the gas giants, where things get spectacular. Jupiter. Jupiter is the largest planet in the solar system, with a mass about 318 times that of Earth. It is also the fastest rotating major planet 1. Jovian day is only about 9 hours and 55 minutes. Combined with its enormous mass and gas-liquid composition, no solid surface to resist deformation, Jupiter is dramatically oblate. Jupiter's equatorial radius is about 71,492 kilometers. Its polar radius is about 66,854 kilometers. The difference is about 4,638 kilometers. The oblateness, the ratio of this difference to the equatorial radius, is about 6.5%. This is so pronounced that you can see it in photographs with the naked eye. Jupiter is visibly squashed. If you look at pictures of Jupiter, you can immediately see that it's wider than it is tall. Jupiter also has turbulent atmospheric bands, the famous stripes of alternating eastward and westward jet streams, and massive storm systems like the Great Red Spot. These atmospheric features are also consequences of the rotation. The Coriolis effect, the deflection of moving air by the rotation of the planet, organizes the atmosphere into these banded structures. The banding, the oblateness, the jet streams, all of it flows from the rapid rotation. Saturn, I mentioned Saturn earlier, but let me be more specific. Saturn has an oblateness of about 10%. Its equatorial radius is about 60,268 kilometers. Its polar radius about 54,364 kilometers. This is the most extreme oblateness of any planet in the solar system. Saturn's rotation is also rapid, about 10.7 hours, and Saturn is less dense than Jupiter, making it easier for the rotation to deform it. Saturn is so oblate that if you saw it next to a perfect sphere of the same volume, you would immediately notice the difference. And Saturn's rings, those magnificent, iconic rings, orbit in the equatorial plane. The rings must orbit in the equatorial plane because the equatorial bulge creates a gravitational force that would drag rings out of any other orbit. The rings of Saturn are where they are because Saturn is not round. Uranus and Neptune are also oblate, though less dramatically so than Jupiter and Saturn, partly because they're less massive and have less self-gravity to be overcome by rotation, and partly because they rotate somewhat more slowly. But I want to go beyond planets and talk about some even more extreme examples, because nature provides us with objects far more extreme than Saturn objects, where the shape deviations from a sphere are so dramatic that they completely change the physics. Neutron stars. When a massive star reaches the end of its life, it collapses and explodes in a supernova. The core that remains, if the star is massive enough, is a neutron star. A neutron star packs a mass greater than the Sun into a sphere only about 20 kilometers across. The density is unimaginable. A teaspoon of neutron star material weighs about 10 billion tons. Many neutron stars rotate incredibly rapidly, hundreds of rotations per second. These are called pulsars, and the most rapidly rotating ones are called millisecond pulsars. The record holder rotates at over 700 times per second. What does this mean for the shape? A neutron star rotating at 700 revolutions per second has surface material at its equator moving at a substantial fraction of the speed of light, about 20% or so. The centrifugal effect at such speeds is enormous. The equatorial bulge of a rapidly rotating neutron star can be significant. The equatorial radius can be several kilometers larger than the polar radius. For a 20-kilometer object, that's a 20% difference in radius, much more dramatic than Saturn's 10%. And in rapidly rotating neutron stars, general relativity is not a small correction. It is the dominant physics. The space-time around a rotating neutron star is dramatically curved, dramatically frame-dragged. The shape of the neutron star is not determined by classical mechanics, but by the equations of general relativistic fluid dynamics in strong gravitational fields. The shape of a neutron star in the full relativistic sense is a solution to Einstein's equations coupled to the equations of state of ultra-dense nuclear matter. It is about as far from round in the simple sense as it is possible to get. At the extreme end, black holes. A non-rotating black hole is described by the Schwarzschild solution to Einstein's equations, which is spherically symmetric. So a non-rotating black hole is, in the appropriate mathematical sense, round. But a rotating black hole is described by the Kerr solution, which is not spherically symmetric. A rotating black hole is oblate, its horizons are not spheres, and a maximally rotating black hole, spinning as fast as physics allows, has an equatorial radius exactly twice its polar radius. Even black holes are not round if they're spinning. The lesson I want you to take from this tour of the solar system and beyond is this. Spherical shape is an idealization that is never exactly achieved in nature. Every real body is subject to rotation, tidal forces, internal mass distributions, geological history, and in extreme cases, relativistic effects, all of which push it away from perfect sphericity. The question is not whether a body deviates from spherical shape, but by how much and why. Understanding those deviations, measuring them, calculating them, understanding what they tell us about the interior and history of a world is one of the most powerful tools we have for understanding planets and stars. The non-roundness of the Earth is not a flaw in nature's design. It is nature's way of recording its own history, written in the language of shape. We've come a long way. We started with a simple question, what shape is the Earth? And we've traveled through classical mechanics, gravity, geophysics, plate tectonics, satellite technology, general relativity, and the interiors of neutron stars. Now I want to bring it all together. I want to tell you what this journey teaches us, not just about the Earth, but about the nature of science, the nature of reality, and the nature of the questions worth asking. Let's review what we found. The Earth is not a sphere. It is an oblate spheroid, bulging at the equator by about 22 kilometers because of its rotation. But even the oblate spheroid is an idealization. The true shape, the one determined by the actual distribution of mass inside the Earth, is the geoid, a lumpy, irregular surface that deviates from the spheroid by up to 85 meters or more, and that reflects the complex geological history and internal structure of our planet. And even the geoid is only a classical description. In general relativity, the shape of the Earth is a four-dimensional curved space-time geometry, twisted by the Earth's rotation through frame dragging, ticking at different rates, at different heights, and deviating from flat Euclidean geometry in ways that are small but measurable and practically important. That is the full, honest, scientific answer to what shape is the Earth. Now, I want to make a broader point, a point about how science works. The history of our understanding of the Earth's shape is a perfect microcosm of how scientific knowledge actually advances. You start with an approximation, a model that captures the most important feature but ignores the details. The Earth is roughly spherical. That's the first approximation, and it's a good one. It's good enough to get the right answer for many questions. How long it takes to sail around the world, why there are time zones, why the sun rises in the east. But then you look more carefully. You make more precise measurements. And you find that the approximation breaks down, not catastrophically, not in a way that invalidates the original model, but in a way that reveals more structure. The Earth is not just spherical, it's an oblate spheroid. Now you have a better model. It captures more of the truth. It lets you calculate things you couldn't calculate before. The precession of orbits, the variation of gravity with latitude, the behavior of ocean currents. But you keep looking, you keep measuring more carefully, and you find that the oblate spheroid is itself an approximation. The real shape is the geoid, the gravitationally complex, geologically bumpy, dynamically changing geoid. Better still. Now you can do geodesy properly, design GPS satellites correctly, understand ocean circulation. And then you look even more carefully, and you bring in Einstein, and you realize that the geoid itself is an approximation. It's a classical description of what is fundamentally a general relativistic phenomenon. The shape of the Earth is, at bottom, a solution to Einstein's field equations. And now you can do precision timing with atomic clocks, design GPS with relativistic corrections, test general relativity with satellite experiments. This is how science works. Not by replacing one model with another, the sphere was wrong, now we use the geoid, but by a sequence of successive approximations, each capturing more of the truth, each building on the previous, each revealing new phenomena and new questions. Every scientific model is an approximation. The question is always an approximation to what precision, for what purpose, and what does the next level of precision reveal? This is something I have always found deeply satisfying about physics. There is always another layer. There is always more structure. The universe has more going on in it than any single model can capture. And the adventure of science is the adventure of finding the next layer, the next level of precision, the next deeper truth. Now let me talk about something that I think is one of the most profound lessons hidden in the story of the Earth's shape. and it is this: local physics is universal. The fact that the Earth bulges at the equator is not a special fact about the Earth. It is an inevitable consequence of rotation and self-gravity that applies to any rotating, self-gravitating body. It applies to all the planets. It applies to stars. It applies to galaxies. The Milky Way is a disk, not a sphere, because of its rotation. It applies to neutron stars and black holes. The geoid, the gravitational equipotential surface, is also a universal concept. Every massive body has a gravitational field. Every gravitational field has equipotential surfaces. The shape of those surfaces reflects the internal mass distribution. This is true for the Moon, for Jupiter, for the Sun, for any galaxy. Gravitational time dilation, the fact that clocks run slower in stronger gravitational fields, applies everywhere in the universe. On the surface of a neutron star, where gravity is 1 billion times stronger than on Earth's surface, clocks run dramatically slower. Near the event horizon of a black hole, clocks approach a complete stop. The effect we see on Earth a few microseconds per day is just the gentle end of a phenomenon that extends to extremes we can barely imagine. The physics we use to understand the shape of the Earth is the same physics that operates everywhere in the universe. That is the real meaning of universal laws of physics. They're not just laws that happen to work everywhere. They're laws that encode the deep structure of reality in a way that applies at every scale, in every context. From the tiny deviation of the Earth's shape from a perfect sphere to the extreme curvature of space-time around a black hole. Let me tell you about another lesson that I think this story teaches. And it's a lesson about the relationship between precision and discovery. The Earth looks round from space. The famous blue marble photograph taken by the Apollo 17 astronauts in 1972 shows a beautiful cloud-swirled sphere. If you didn't know what you were looking for, if you had no measuring equipment, just your eyes, you'd say, it's round, perfectly round, case closed. But looks round to the naked eye is a statement about measurement precision. The human eye can distinguish shapes to roughly 1% precision, maybe a bit better for trained observers. The Earth's oblateness, the equatorial bulge, is about 0.3% of the Earth's radius. Below the threshold of naked eye detection, of course, it looks round. Looking round is consistent with being 0.3%, not round. This is why precise measurement is the heartbeat of physics. The most important discoveries in the history of science have often come not from finding something completely new and unexpected, but from measuring something familiar to greater precision than before and finding that the more precise measurement disagrees with the theoretical prediction. The precession of the perihelion of Mercury is a famous example. Newton's theory predicted the orbit of Mercury should precess at a certain rate due to the gravitational perturbations of the other planets. But the measured precession was slightly faster than Newton predicted by 43 arcseconds per century. Not a large discrepancy. 43 arcseconds per century is a tiny, tiny difference. But it was real, and it was explained only by Einstein's general theory of relativity. A small discrepancy in a precise measurement revealed that Newton's gravity was an approximation to Einstein's deeper theory. The GPS relativistic corrections are the same story. If you didn't need GPS to work to meter-level precision, you could ignore the relativistic effects. They're small. But for GPS to work, you need meter-level precision or better. And at that level of precision, the relativistic effects are not small, they are dominant. The desire for precision forced us to confront the physics of curved space-time in a very practical engineering context. The lumps in the geoid are the same. If you only need to know your position to within a few hundred meters, the geoid doesn't matter, the spheroid is good enough. But for precise geodesy, for the precise determination of sea level rise due to climate change, for monitoring the subtle shifts of tectonic plates, for calibrating oceanographic measurements at that level of precision, the geoid is essential. Precision demands truth. The more precisely you try to describe or measure the world, the more you are forced to confront the real, full complexity of what's there. Every idealization, every simplification, every model, every approximation eventually breaks down when you look carefully enough. And every breakdown is a discovery. So what is the shape of the Earth? Let me give you my final answer. The shape of the Earth is a living record of its history in physics. The oblate spheroid shape is a record of the Earth's rotation, a memory of the angular momentum inherited from the spinning molecular cloud that gave birth to the solar system. The geoid lumps are a record of the Earth's interior, the density variations in the mantle and core, the scars of ancient collisions, the signatures of convection currents deep below the surface. The glacial rebound is a record of the ice ages the Earth's crust, still bouncing back from the weight of kilometers of ice that covered it thousands of years ago. The tidal deformation is a record of the moon's gravitational influence, the gentle, twice-daily flexing of the solid Earth. And the space-time curvature is a record of the Earth's mass, the bending of the four-dimensional fabric of reality by the presence of this 6 × 10, 24-kilogram ball of rock and metal, a curvature that affects every clock, every satellite, every GPS signal that passes through this region of space. The shape of the Earth is not round. It is a palimpsest, a document written over and over by the forces of physics and the accidents of history. To read it properly, you need Newton and Kepler and Einstein and Gauss and all the many scientists who have spent their careers measuring it with ever-increasing precision. And the reward for reading it, the reward for caring about those 22 kilometers of equatorial bulge, those 100-meter lumps in the geoid, those 38 microseconds of daily relativistic correction is a richer, deeper, truer understanding of the planet you live on. An understanding that connects the ground beneath your feet to the stars above your head through the universal language of physics. The Earth is not round, and that, my friends, is one of the most wonderful things about it. Because if it were perfectly round, if it were a featureless, smooth, perfectly symmetric sphere, it would have no story to tell. No history written in its shape, no record of the spinning cloud that birthed it, no memory of the ice ages that scarred it, no signature of the moon that pulls it, no testimony to the curved space-time that surrounds it. The lumps and bumps and bulges of the real Earth are not imperfections. They are data, they are history, they are physics, they are the universe writing its autobiography in the shape of a world. And the fact that it took us thousands of years, from the first Greek philosophers who argued about the Earth's shape, to Newton, who predicted the equatorial bulge, to Einstein, who showed us the curvature of space-time, to Grace satellites that mapped the geoid with millimeter precision, the fact that this question is still being answered, still being refined, still yielding new insights, that is what makes it a great scientific question. Not, is the Earth round, but how non-round is it, and why? And what does the precise shape tell us about physics and history? That's the question worth asking. And the answer is magnificent.